Now we are changing the topic. We want to determine angular momentum, torque and kinetic energy of a rigid body rotating about an axis. Okay, it's a rigid body. It's three things we are want to find out. One is the angular momentum, another is the torque, and third is the kinetic energy. Till now we have discussed these two things, angular momentum and torque, for a particle. Now for a rigid body, because these relations will be in connection with the moment of inertia. That's why. And the kinetic energy which we will be finding out, that is mainly the rotational kinetic energy. Okay. So let us consider a rigid body. Again I am considering the first figure. Today only we have discussed this figure. Once we have already discussed. That is, let us consider a rigid body made up of a number of the point masses m1, m2 and so on up to mn, and their perpendicular distances from the axis of rotation AB is r1, r2 and so on up to r. What will happen? If the body will rotate, I have told you, if you remember, if the body will rotate, every point mass will move in the circular path. Okay? And in every circular path, what will happen? The linear velocities for the first particle it is v1, for the second particle it is v2, for nth particle it is vn. Okay, they will always be acting in the tangential direction. Tangential. For example, I just show. Suppose this will make a circular motion like this. Like this, a circular motion. Linear velocity will be acting tangentially. But mind this, one thing we have to remember. In case of this rotation, every point mass will make the circular motion, and here the value of omega will always remain the constant for every particle, but the linear velocity will be changed. Angular velocity will remain the same, but the linear velocity will be different. That is why linear velocity will be different, because v1 is equal to r1 into omega, r2 into omega, r1, r2 and so on. These are the different. That's why we are taking it like this. Very clear? So what we are getting? v1 is equal to r1 into omega, v2 is equal to r2 into omega and so on. Okay? We are considering these points. So let us now first find out the angular. Our first discussion is regarding angular momentum. Okay? Angular momentum. First I write it like this. Angular momentum of the first particle. Let us find out the angular momentum of the first particle. First particle is here. That is L1 is equal to P1 into R1. Now you will say how? How? I am telling you. I hope you all remember in our last class, it is for a reminder. L vector is equal to R cross P. Then R into P into sine theta. Okay? Here P will be in the direction. P is what? Linear momentum. P will be in the direction of the velocity. Velocity and radius are always perpendicular to each other. Okay? That means here what we will write? R into P into sine 90 degree. Why? Because angle between R vector and P vector will be 90 degree. That means how much it will be? It will be R into M into V. Okay? That means here also I will write what? M1, V1, R1. Just follow this. This we have already discussed in the last class. Just it is for your reminder. As a reminder I am using it. In our last class, R cross P. P is the linear momentum. Linear momentum का कौन सा डायरेक्शन रहेगा? जो velocity का डायरेक्शन रहेगा. और velocity tangential डायरेक्शन में है. Tangent हरदम रेडियस पर परपेंडिकुलर होता है इसलिए. So m1 v1 r1. Then how much it will be? It will be m1. v1 is omega r1 into r1. Or we can write this is equal to m1 r1 square omega. Look. So obviously if it is L1 is equal to m1 r1 square omega, then I can write similarly L2 is equal to m2 r2 square omega and Ln is equal to mn rn square omega. Okay, so what is the angular momentum of entire body? That is L1 plus L2 and so on up to Ln. All will be summed up. How much it will be? It will be m1 r1 square omega plus m2 r2 square omega and so on mn rn square omega. So what we can write? m1 r1 square plus m2 r2 square plus so on mn rn square omega. Or I hope you all remember today we have discussed L is equal to, what is this? Summation mi ri square, I is equal to 1 to n. This much, the whole thing in the bracket into omega. Or we can write L is equal to I into omega. Because I hope today only we have discussed this whole bracketed term is equal to I. Look at this. So very simple and plain discussion. Look at this. I hope all of you have got it. That is a very important relation we are getting. L is equal to I into omega. L is equal to I into omega. Okay, angular momentum is equal to I into omega. So angular momentum discussion is over. Now I hope you have completed, you have seen this. I am removing this from here. Let us now come to our next part of the discussion, that is rotational kinetic energy. Rotational kinetic energy. Let us consider the kinetic energy. What about the kinetic energy? First of all, here again, kinetic energy of first particle. Kinetic energy of first particle K1 half m1. It's simple, m1 v1 square. That is half m1 r1 square omega square. Okay? So what we can write? Rotational kinetic energy of entire body. Entire body will be how much? Capital K R. I write a symbol here, capital K R. R for rotational. That is equal to K1 plus K2 plus dot up to Kn. Don't confuse between radius of gyration and this here. That's why I have written it only K. That is equal to, for first particle m1 r1 square omega square plus half m2 r2 square omega square and so on up to mn rn square omega square. Look, because omega is always a constant for all, that's why this is how much we can write. This is here half omega square, here m1 r1 square plus m2 r2 square and so on. Mn Rm square. So obviously Kr is equal to half here I into omega square, because I have told you this bracketed term is I, moment of inertia. See, rotational kinetic energy, translatory kinetic energy is half mv square, rotational kinetic energy is half I omega square. See this. This is about the rotational kinetic energy. Alright? If the pure rotation is there in a body, then the rotational kinetic energy will be taken into consideration and it will be half I omega square. I hope all of you got this point. Okay, in the next lecture I am coming to the torque. What about the torque of this body? Right?